Okay, give me just a little bit of time here. I want to show you something. Close those up real quick. I'll give you a chance. I promise I'll give you a chance to work too, but I want to just kind of take this a little piece at a time. You guys can teach this to your peers when they get back. This isn't a big deal. Let's take a quick look at, so everybody close those up real quick. Give me like 15 minutes and then I'll let you work. Just want to go through a couple things here. So I want to look at some rational functions that are a little bit, well, let's start off by taking a second look at some problems like this, right? You guys did some, or you're currently working on some like this, where we took rational functions of this form and we divided them out and we wrote them as transformations of the inverse function 1 over x. And that's kind of what you're practicing. And that's fine. That's not a bad way to do it. But there's an alternate way I want to show you. That's really not the way we do it in calculus, for example. What we'll do in calculus instead is we'll just leave them as rational functions like this, and we'll draw a skeleton. We'll sketch a skeleton of the function based on its asymptotes, and then just pick a couple test points and get a quick sketch of it. That we do a lot of curve sketching in calculus. So without having to divide this out and transform it then, can anybody tell me what some characteristics of this function that might help us guide the graph?
X cannot equal 1.
Okay, x cannot equal 1. What do you think is going to happen at x equals 1? It's whatever the function is undefined there. Anybody want to take a guess at what the function might look like there? What's going on at x equals 1? Yeah, when you divide by 0 like that, it doesn't work. But what's it translate to in terms of what the graph is going to look like? Any ideas? Okay, well, we'll find out. We'll graph it and we'll see. And then we'll kind of start to put some, we'll put some characteristics together that we can make predictions about from the rational function. So that's one question that we got. We want to know what goes on at 1, because that's a 0 of the bottom. Can you tell me one point for sure on that graph? What's another point you can look at and say, oh, I know one place it's going to go. There's one point it's going to go through for sure. Is the point what?
3, -3.
What's going to happen at -3?
That's going to be.
Yeah. Look at the top here. So the 0 of the bottom is at 1, isn't it, right? And we don't know what's going on there. We're going to find that out. What's the 0 of the top? The numerator. -3. So what's the value of any function that has 0 in its numerator, as long as it doesn't also have 0 in its denominator? That's indeterminate. But if a fraction has, if the numerator is equal to 0, what's going on there? What's the value of the fraction? 0, right? So we know that one point on this function is going to be at x equals -3, the fraction, which is the function, is equal to 0, right? So that's one point that we know for sure. Oops. That it's going to go through. Oh, man. Wrong one. So one point we've got is at, was it -3?
Yes.
-3, 0. So right there, right? But we don't know much else. So let's go ahead and graph this thing and see what we get. The function was x minus 3 over x plus 1. Okay.
X plus 3 over x.
X plus 3 over x minus 1. There we go. Okay. So there it is. X minus 1. Okay, so what's going on? So sure enough, it does go through that point right there. There's our point, negative 3, 0. What's happening at x equals 1?
It's asymptotic.
Okay, it's asymptotic, yeah. So we know, thanks. So a 0 of the bottom like that, where the function's undefined, gives us a vertical asymptote, right? Okay, good. The rest of the function is a little bit mysterious. So let's take one other look at how we could determine. We know we've got this vertical asymptote at 1, but there's a couple things that could be going on with that, right? So if here's our, it was a positive one, right? So we know we've got this vertical asymptote, but there's a bunch of things the function could be doing. It could be going up on this side and up on that side. It could go down on this side and up on that side. There's all kinds of possible things that could be happening there, right? So which one is it going to be? Well, one way we can tell, and this is a pretty advanced topic, but I want you guys to see this. We'll see a lot of this stuff in calculus, is we could take a limit of the function and think what a limit means. Now, we've talked a little bit about this. A limit just means what value is the function approaching as x does something. So what about as x approaches 1 from values less than 1? Okay, so the way we would denote that is by saying 1 minus. So we're approaching 1 from the negative direction, right? So as x approaches 1, what does the function do? Well, we can see that as x approaches 1, the bottom is approaching 0, isn't it? Right? And so we can't ever actually get to x equals 1 because that would give us a 0 on the bottom. But that's the beauty of limits. We'll talk a lot more about this in calculus, but here's the concept that we mentioned earlier in the year that kind of introduces us to limits, is this idea that if I'm going to cut my distance to the door, remember this, in half every step for the rest of eternity, mathematically, I'll still never get to the door. Right? I'll get closer and closer and closer. Each step gets smaller and smaller and smaller. But this is always the limit of my motion. This is the only place moving in this direction that I never get to is the door itself. If I had an infinitely fine point on a pen, I could make a dot as arbitrarily small as you want to, but there's no dot that's not physically on the door that I wouldn't eventually step on. Does that make sense? There's no place, there is no point next to the door. There's always going to be an infinite number of points between any point and the door, right? And so this concept of a limit then is just this idea that, we're just gonna go closer and closer and closer to that. We never get there, but let's see what happens as we do. Okay, so as x approaches 1 from the left, what number does the top approach?
4.
Yeah, it just approaches 4, doesn't it? Right? Positive 4. Okay. What number does the bottom approach?
1.
As x approaches 1.
0.
Okay, it approaches 0, right? But it never gets there, does it? Okay.
You get 4.
Because 1 plus 3 is 4.
Oh, okay.
On the bottom, we approach 0, but it's not going to actually be 0. I want to be more specific. I want to know, is it going to be slightly negative or slightly positive?
Slightly negative.
It's going to be slightly negative, isn't it? Because I'm taking a number slightly less than 1 and subtracting 1 from it. Imagine we take 0.99999 minus 1. I'm going to get negative 0.00, right? 0.00001, right? So here's how I always say this. And this is kind of, I don't really know if this is in a textbook or not, but this is a good way to do it. I always just put a negative superscript by the number 0 to tell you that, yeah, it's infinitesimally small. It's approaching, it's approaching 0, but it actually is a number. It's not 0. It's still negative, right? So what do you think happens when we divide a positive number, of any size by a vanishingly small negative number? Yeah, as the bottom of a fraction gets smaller and the top stays the same, what happens to the size of the fraction? It gets larger and larger and larger, doesn't it? So what is the magnitude of this fraction approaching? Yeah, we know that it's, does that make sense? That it's approaching infinity because the top is staying at 4, but the bottom is approaching 0, right? That make sense? I mean, and just take if you want a model of that, just take real numbers. Let's just take 10 divided by, by 0.1. 10 divided by 0.1 is 100. Well, what's 10 divided by 0.01? 1,000. 10 divided by 0.001 is 10,000, and so on and so forth, right? It's just getting bigger and bigger and bigger. But what's the sign going to be? Well, we'll just follow our sign rule. I've got a positive numerator divided by a negative denominator, so what's that give us? Negative. That tells us something, right? That tells us that as we're approaching 1 from the left, from the negative direction, our function is going to sweep down to negative infinity, right? Well, let's do the same thing as we approach zero from the right. If I approach 0 from numbers slightly bigger, or sorry, 1, not 0. If I approach 1 from the right, so I'm approaching from numbers greater than 1, I'm backing down to 1. I'm going to go at 2, 1.5, 1.1, 1.01, 1.001, etc., right? What do I get then? Once again, I'm going to get 4 on the top. But now what number am I getting on the bottom? I'm approaching 0, but what's the sign going to be? Positive. Yeah, so we'd call it 0 plus, right? And so this time, I'm going to get an infinite answer, right? It's approaching infinity, but the sign is going to be positive. So if we approach from the other direction, it's going to do that, right? And we know in this case that f, we can look at the 0 of the top, right? 0 of the numerator. We know that f of negative 3 equals 0. So if we want to be a little more precise with this bottom part here, we know that it's actually going to go through that point. So it's going to go something like that. Okay, make sense? Okay, we don't really know, we'll be able to tell a lot more here soon, but that's just one trick that I wanted to introduce you to today, is this idea that, okay, so we know that we're getting a 0 on the bottom, and we can use this kind of a limit approach. Just pick a number that's approaching this number from the right or left and see what the sign's going to be of the overall function to see if it's going up to infinity or down to infinity. Yep.
So essentially you can use the numerator and denominator to determine the vertical and horizontal asymptotes.
To determine the vertical. We don't know about the horizontal yet. We haven't talked about that yet. That's coming up. But there is a way to quickly do that too. I'm not going to show you that rule today though. Okay, what about something like that one then? Just make a prediction for me. We're not going to do too much with this today. I don't want to do, but what are some characteristics you can tell me about that function? So if I could maybe do what's one thing that's going on there? Tell me something. Emily, tell me something that's going on with that function.
You have to
Okay, I have 2 factors on the top.
Yep.
Mhm. Okay, but I want to know, now tell me either a point that's on the curve or tell me where there's an asymptote. Somebody. Okay, how come? Okay, because that's a 0 of the bottom, right? Okay. Now we gotta be a little bit careful with that because we're gonna see an example here soon where we gotta be a little more specific. But so there's our vertical asymptote. Comes from the bottom. Now what about the numerator? What's something? Gabe, tell me something. What does the numerator tell me? What's one thing it tells me?
There's 0 at positive 1.
Okay, so a positive 1, I've got a 0 of the function. Good. So right here, I know that it's going through the point x equals 1 because that makes the numerator 0. What's another one? Negative 5. Okay. So right there. Good. And then if I wanted to know whether it's going up or down, what kind of a limit, what could I do? Like, what kind of a limit could I take here? I could take the limit of my function as x approaches what? What's one limit I might want to take if I want to know how is the function sticking to that vertical asymptote? What do you think? Elizabeth, you have an idea? I want to know, I know I've got the asymptote at -1. But if I want to know what it's doing, let's say an ant's walking along the function from the left. What am I going to be approaching here? It's got to be 1. Okay, anybody want to help around with that? Negative, 1 minus, right? Okay, and what's that mean? That 1 minus, all that means is, yeah, we're approaching a value of 1, but we're approaching from this direction. If I were to say instead, if I were to say the limit of x plus 5 over x minus 1 as x approaches, over x plus 1 as x approaches 1 plus, now we're approaching 1 from the positive direction, right? So from the negative direction, what's going to happen? I'm going to get on the bottom 0 what? Should be -1, shouldn't it? Sorry. What am I going to get on the bottom?
0.
But not just 0, I have to know the sign. 0, it's going to be 0 minus, yeah, right? Because it's going to be something like -1.1-ish, right? Plus +1. It's going to give me a little bit of negative left over, isn't it? So I'm going to get a 0 minus on the bottom. What are the signs? And what do I get up here? And really all I need to know, I don't even need to know what the numbers are. I just need to know what the signs of those numbers are going to be, right? I'm going to get a +4, right? I'll just put a 4 for now. But all I care about is that it's positive. And then what's this going to be? -1 minus 1, -2. So what's the overall sign at the top?
Negative.
Divided by negative is positive. Okay, so that means from the left, we're approaching positive infinity, right? So it's doing that kind of a thing, evidently, right? You get the idea? As we approach from the left, we know it has to go through that point, and it's going to stick to the asymptote going upwards. How about over here? We're going to get 0 plus on the bottom, aren't we? If I approach -1 from the right, I'm going to get like -0.99 plus 1 would be +0.0 something, right? So I get a 0 plus, and then I get the same numbers at the top, don't I? So this one's going to be negative over positive is negative, right? And it's going to do something like, maybe like that, right? Get the idea? Okay? All right, good. How about that one? What can you tell me about that one?
Do we get to work all the time?
Oh yeah, that's probably good. You guys can work.
Yeah.
That'll get you going.
Thanks.
Yeah, we'll pick up with that later. I just want to introduce you.